So Radhika,
Hello, am I audible?
yeah, over to you.
Okay. So, good evening, everyone. Filled with immense pleasure and privilege, I welcome you all to the webinar on the present status and future prospect of EV and renewable energy, brought to you by IEEE IEEE Joint Chapter Kerala. Without further ado, I like to invite Dr. Biju K, Treasurer of IEEE Kerala Section, to give a brief insight on the topic of the session. So, please.
Thank you, Radhika. Good evening, people across the globe at the different time zones. And good morning, Dr. Abhijit Chowdhury, today's resource person for us. So this is the webinar in a series of association between our joint chapter, IEEE joint chapter Kerala and Robert Bosch, Bangalore Limited. Because we have started an association to collaborate in research and other kind of activities, and we are in the process of developing an MOU between our chapter and Robert Bosch, and we started these webinars and these workshops in this before we just opening up to the hackathon last week by Mr. Pradeep from Robert Bosch, and this is a second webinar in this series. And today we have an expert, an apt person to talk in this area of electric vehicles and renewable energy. And all of us know how much relevant the topic is, because there is a lot of trend now towards renewable energy and electric vehicles. And so I am not going deep into the bio of Dr. Abhijit Chowdhury, because formerly our chapter chair, Dr. Bijina Kunjum Madam, will formally introduce Abhijit Chowdhury. And with this note, I invite Dr. Abhijit Chowdhury and all the participants of this webinar to this session. Thank you. Over to Radhika. Radhika.
Thank you, sir. Now, I'm honored to welcome Dr. K. Bijana Kunju, the chairperson of IEEE IEEE Joint Chapter Kerala, to welcome our renowned speaker, Dr. Abhijit Chowdhury. Ma'am, please.
Good evening, ladies and gentlemen, and good morning to the very respected speaker of the day, Abhijit Chowdhury. We welcome you to this special webinar we are conducting, as Biju said, in association with Robert Bosch. This is one of the big hot topics that we are looking at, the electric vehicles, and we have got the apt speaker for the day. We have Abhijit Chowdhury, who is a graduate from NIT Agartala. He had graduated in 2007, and then he did his post-graduation from IIT Mumbai in 2011, and continued to do his PhD from University of Montreal, Canada, QC, in 2015. And he has wonderful experience in industry also, where he did his experimental power grid center at Singapore, as well as he was part of G or ABB and General Motors. So this is a fantastic day for us when we are listening to him, when as he is part of the Center for Technology Innovation Controls at the Research and Development Group of Hitachi Limited. So he is a person who's doing research, experimenting with it, and is associated with the industry also. And none other than him can show us the cutting edge technology, as he is also an associate editor of the IEEE Transactions on Transportation Electrification. So it is the rare opportunity for us to listen to a person who is a blend of all: an expert in EV, a researcher by passion, and a practicing industry person by profession. Welcome, Dr. Abhijit Chowdhury. This is a great day for us.
Thank you, Dr. Vijana, Madam, for your introduction, and also thank you to Dr. Biju for your invitation for this session. Thank you.
So,
So you can share your screen now.
Yes. Shall I share my screen now?
yes, yes, you can.
Yes, sir.
Okay. Thank you. Is it visible?
Yes, sir, it is.
It is visible.
Okay. Good evening to all. And once again, thank you to Dr. Biju for inviting me for this session. Just for a quick introduction, as we know that the global target is set to reduce the carbon emission by 40% by 2030 as per Paris agreements. So different governments from countries are taking different initiative and offering subsidies to promote renewable energy related business and smart and energy efficient transportation system. So in this session, I'll try to discuss about the growth in EV and renewable energy related storage industry for past couple of years and some of the research areas which are related to this field. So basically I have divided the slides into three sections. The first section I will discuss about the EV industry and their growth. The second section I have discussed about the non-EV related energy resources. And the final section I have discussed about some of the key technology or the challenges that we need to face to develop such kind of to achieve such kind of goal. So in these slides, it's basically shown the growth of EV industry over the past 10 years. So here it shows the stock of EV is not the sold amount, it is the stock that we currently have for EVs. So EVs, in EVs, we have categorized in two parts. One is battery electric vehicle, and the second one is plug-in hybrid electric vehicle. So as we have seen that there is a gradual increase in EV industry over the past 10 years, and majority of the EV market is dominated by China till now. But maybe in next 10 years, other countries will grow their EV stocks and more emerging technology will come into pictures. So if we consider 2019 scenario, so about 45% of the EV stock is now currently occupied by China, and majority of them are battery electric vehicle, and there is a small percentage in plug-in hybrid electric vehicle. If we consider other countries like the Europe or US, they are also growing, but they are not up to that scale that China has built up their infrastructure or their growth in that market, in the renewable and the EV market yet. But we are expecting that over the next 10 years, there will be a tremendous growth in EVs in other countries, including India. If we have lots of EV, we need to charge them, and for that we need to build up our charging infrastructure as well. And here there are three pie chart. It shows the stock or the install capacity of the EV chargers. As we know that EV charger basically can be divided in two categories. One is the slow charger and another one is the fast charger, which is generally called DC charger. So the slow chargers, again, we can either can be installed in our homes, because most of the battery electric vehicles, when we return home from work, we need to charge overnight so that we can use next day. So as you can see that the privately owned chargers are quite a higher percentage compared to publicly accessible chargers. So the privately owned chargers are about 6.5 million, and where for publicly accessible chargers are about 0.6 million. So overall, the slow charger, we can see we have a stock of 7.2 million. And for the fast charger, we have around 0.3 million. So in that case also, as we have already seen that China has a very good market for EVs, and they have already sold a lot of EV compared to other countries. So in terms of the charger also, their percentage is also very high. So if you consider the slow chargers, we can see about around 35% is basically in China. Similarly, the publicly accessible chargers, about 50% is occupied by China, and DC fast chargers are also about 70% is 70 to 80% is now occupied by China. So after the car, so there are different type of electric vehicle. One is our day-to-day commute vehicle, the small cars. Then there, the second category is like bus. So here for the bus segment also, we can see there is a huge stock or the sold amount of electric buses in China compared to the other countries. So there may be around 60 to 70% more number of EV bus that is sold in China to compare to other countries. But in future, there is a gradual increase in EV bus in other countries also, and by 2030, we are expecting that there will be more bus will be sold in other countries compared to past 10 years. Here it shows the another third category of EVs, that is medium and the heavy duty trucks. So again, here we can see that majority of the trucks or medium duty vehicles that are sold are in the Chinese market. So they have a very high growth or the capacity in the medium and the high duty truck segment as well. But other countries also now gradually they are going to increase their capacity, as both the government and other private sectors are coming into picture to take different initiatives. This slide shows the growth for last 10 years, which is up to 2019, and the growth that we are expecting over next 10 years. So here there are basically three segments. One is 2019, that up to 2019 the EVs that are sold. Then we are expecting the growth we are expecting in 2030. So in 2030, the expected growth in EVs we have differentiated in two parts. One is the stated policy scenario. Stated policy scenario includes all the policies that we are currently having from the government. And the sustainable development scenario includes different initiative which different governments may take to achieve the climate change agreement as per the Paris Agreement, to reduce the global temperature, to limit the global temperature rise below 2 degree by 2030. So in this segment here, you can see that again we have divided the growth in several parts. One, the blue color shows here the plug-in light duty vehicles. Then plug-in light duty vehicles are categorized in two parts. One is battery electric vehicle and the plug-in hybrid electrical vehicle. And we have light commercial vehicle that like a pickup trucks. Then we have buses, both in battery electric and plug-in electric, and we have truck segments where we have both again battery electric and plug-in hybrid electrics. So if we see the bar chart, so majority of the growth we can see in both in plug-in electric vehicle, in passenger light duty vehicle segment, and hybrid electric vehicle. So these are the two sectors that we are expecting that there will be an increase in the stock of EV about 15 to 20 times more than whatever we had until now. So as we are going to have more EVs, then we need to charge them, and for that we need a lot of electricity from the grid, and for that we need a lot of power. And this slide shows different the power requirements from the utility grids, the increase in the power requirement from the utility grids for over next 10 years. So as we can see that until 2019, where we had a requirement of 110 terawatt hour of power by 2013. If we follow the growth trend as we have shown in the last slide, we are expecting that the power demand will increase about 15 to 20% to about 600 terawatt hour. And the one of the interesting part is that here you can see that this segment does not only includes the EV vehicles, it also includes two-wheelers and three-wheelers. Like third world countries and the developing countries, they use a lot of two-wheelers and three-wheeler vehicles. And as we go for electrification of the transportation system, the business will be this business will grow much more compared to the car normal passenger vehicle, because they are cheaper than the normal electric vehicle. And so we are expecting that these two areas are also going to grow at a much higher speed that we have seen over last 10 years. The second chart shows the power consumed by the charger. So again, as similar to the electricity demand by different vehicles, as we need to charge them, so does the charger will need the power, and we need to consume from the electricity grid. And for our next 10 years, we can see that there will be a high demand from electricity that they need to take it from the grid. And again, they are divided in different sectors like two-wheelers or the three-wheeler, the buses, then low duty vehicle, the privately owned chargers, the public fast chargers, and the chargers for the trucks. And the third section shows the electricity demand by countries. And similar to the charger or the EV electricity demand, the countries, based on their production of EVs or the consumption of the EVs, they also need to supply electricity to charge the EVs. And for that also, we can see there will be a huge demand of electricity from requirement coming from different countries. And as we can see, the growth of EVs is very high in China. So there will be a huge requirement of electricity related to EV industry over 10 years in China. But the other countries are also coming up for so we are expecting that there will be a high demand of electricity for other countries as well. So the last curve, the fourth one below at the bottom, it shows the displacement of the combustion oil. Because we are using more EVs, so there will be a reduction in IC engine driven vehicles. So there will be a so the consumption of the regular fuels, the petrol or diesel, will go down. So here it shows the reduction in the conventional fuel for the transportation system, and it shows million barrel per day. So as we are increasing as we are going for more EV related transportation system, so the the uh, the energy or the fuel that was required to drive those vehicles will go into more into electricity compared to combustion oil. So the requirement of the oil will reduce. So here, proportional to the reduction in the IC engine vehicle, so the oil requirement will also go down. So now we'll go to the second part of the presentation, which is non-EV related energy storage system. So related to renewable energy, as we know that due to intermittent behavior of the renewable energy like solar power, which is not available all the time. So at the night we don't have any power. Similarly, for the power coming from wind energy is not available all the time. So we need some kind of buffer which can produce energy when this type of powers are not available from renewable energy. So for that purpose, we need energy storage devices, and so the batteries. So apart from those kind of application where we need a buffer for renewable energy, we also need this type of energy storage, stationary energy storage equipment for grid support. Like if there is a sudden collapse in grid, then we need to supply. We need some power to. We need some backup power to start the production of generator again for the black start operation. So for different type of application, for as the renewable energy is increasing into our power grid, and to support the normal utility grid, we need some kind of backup power supply. And for that reason, we need stationary energy source, which may be supplied from batteries. So here it shows the stationary energy source or their installation over past 10 years. So here we can see that for stationary energy related storage, Korea has a very high installation capacity over past 10 years. But last year in 2019, there was a reduction in the installation of this type of stationary storage equipment because there was some safety related issues. So they cut off some of their installed energy storage, stationary energy storage plans, and also they stopped the new installation of this type of system. So for past 1 or 2 years, there was a slight reduction in the installation capacity of stationary energy related sources in Korea, but we are expecting that it will increase gradually for next 10 years as the safety related issues are solved. Other than Korea, we have China, US, Germany, and other countries which are also installing this type of stationary energy storage equipments to their grid to support their utility. This slide shows the two application of stationary energy storage. The first one, as we have discussed, is for grid support, like for black start or to support the renewable energy due to their intermittent behavior. The second one is behind the meter, which is basically are installed in homes. So as we know that if you have, we can install solar in our homes, and uh, we can sell that solar energy to the grid. But all in different countries, different policies, the government has different policies, so we can't directly sell the solar power to the grid. And for that, we can store this power to a battery, and then we can use it for our own purpose. So for that reason, behind the meter type of application is also growing. But the grid scale application or behind the meter type application, all are driven by government policies. So if the government give good high incentive to industries, so they try to install this type of technologies or to the household, for the household application. But if there is no such incentive coming from the government, again the application and the installation capacity goes down. So these are highly dependent on the government policies. So in short, if we see the non-EV related energy storage installation and the different policies, here are the main feature. So addition of the storage system with grid related services like transmission and distribution deferral together with the balancing circuit is increasing gradually. European CEP in 2019 approved the transmission and distribution operators to own and operate storage under certain circumstances. China from 2019 onwards do not allow transmission and distribution companies to include the cost of their storage installation into the transmission fee. So that's why there is a decrease in the installation new installation in China for stationary energy equipments to support grid. And if you see, US, Germany, and France are planning to make regulatory changes to include storage as a transmission asset. Other than that, Australia, Chile already made some changes to include storage in their transmission under certain condition. So we have seen two applications or the growth. Uh, One is in renewable energy sector, another is EV sectors, and both of them requires batteries. So battery is one of the most critical part of renewable energy system or the integration to the grid. As we know that the prices of the batteries are going down, and as we have seen that there will be a very high demand for EV related batteries, the cost of the battery will go down significantly. But there is a huge problem after use problem of the battery. So what we are going to do once the battery lifetime is gone? So for that, there are different business plan that can be considered. So in this slide, the battery recycling scheme is explained. So once the battery is manufactured and it is installed in the the new battery is installed in the EV. If we use it up to certain time, and once the battery properties degrades and is not qualified for the EV application anymore, then it is generally taken out of the EV, and a new battery is generally replace the old batteries in the EV. So now the old battery that we have, either we can destroy it or just throw it, or we can take out some important parts from the batteries like the electrodes. So this is called the raw material extraction. Or we can use that battery and we can refurbish it, and we can use that refurbished battery for other non-critical application, like for stationary energy storage application. So EV batteries are very high spec, so they have to be very energy efficient. So lithium batteries are used. They have to be very compact and lightweight, so that so that it doesn't uh, increase the vehicle weight too much. But for stationary application is not so critical, because we don't have much restriction in space or the weight. But as there will be a building up on the stock of EV batteries, which are very high graded, these batteries can still be used for non-critical application, generally for stationary energy storage application that we have discussed. So this is defined by the second life application of as energy storage. So the lithium batteries can still attain a total usable capacity of 80% after 5 years of usage in EVs, and self-discharge rate of 5% over 25 hours, which makes them a perfect choice for stationary storage application. So once the capacity of the batteries go down below 80%, then we can replace that battery with a new one for EVs, and we can refurbish that old battery and we can use for stationary application. And this second life battery cost is much more lower compared to a new battery, so which will reduce the total installation cost of the stationary applications. In 2025, the second life used batteries could be 30 to 70% cheaper than the new battery, which can reduce the system cost considerably for large storage system. Based on the present growth trend in EV industry, there could be 200 gigawatt hour capacity of second life battery available per year by 2030. In Japan, Nissan has already partnered with Sumitomo Corporation to use Nissan Leaf batteries for their stationary distribution and utility scale application. However, no proper industry standards are there till which go related to the second life of the batteries. So there is a huge perspective or the business area regarding the second life batteries. So how we can use those batteries, and what are the technologies, what are the factory plans, how can we refurbish those batteries, and we can use for other application. So regarding renewable energy or EVs, some of the key technologies or the upcoming technologies that we can consider is like high power density. As we know that the EVs, the space requirement is very high, and the density also. So we need to keep it as the density we need to make as high as possible. So gallium nitride or silicon carbide based device-based converter design is a critical issue or the technology which can be considered for both DC to DC converter or DC to AC converter for the motor drives. Then the second interesting technology is like a in-wheel motor drives to reduce the space consumption. So currently for EVs, we have a separate DC to DC converter than DC to AC converter, which drives a vehicle, the motor, and this motor output is shaft is connected to the wheel. So there is a long drive train for EVs which consume a lot of space. But if we can install the whole drive system into the wheel of a vehicle, so it will reduce the space, and this space, the vacant space, can be used for other purposes. So that is one of the emerging research area. Basically this type of research are already going on for past couple of years. The third one is very important to increase the charging voltage to 600 volt or higher for fast charging application. So currently we are using around 600 volt and less DC link voltage. But if we want to go for a fast charger to reduce the current demand, we need to increase the DC link voltage 800 volt or higher. So the automotive companies are planning to increase their DC link voltage to 800 and higher for fast charging application. The topology and control system development for high power charger like flash charger 150 kilowatt or higher. For currently for automotive application we have different specification based on country. Like in Japan we have CHAdeMO standard, which is up to 400 kilowatt of the maximum power possible charging power is 400 kilowatt. In US we have CCS, CHAdeMO, and Tesla. They have their own proprietary charging system. In China they have GBT type of charger, which is about 200 kilowatt. And currently there is another configuration or the charging standard coming, combining the GBT and CHAdeMO, which can increase the power rating to 900 kilowatt. So all these type of charger, we need very efficient, energy efficient, and technology to support the development. So that is another key area of research. And another fast charging application is for buses, because for highway bus or our local intercity bus, we need to charge the buses at a very short time. So there are only two for the bus application. When they reach any terminal, then they have a longer time to charge. But for intermittent charging, when they're in any public stop, they need to charge at a very fast pace. So it is about 10 to 15 seconds. So for those type of application, ABB has already developed 600 kilowatt flash charger. So they charge at 600 kilowatt for 10 to 15 seconds. And for such kind of application, we need a lot of power at a very short time. So we need to develop our technologies accordingly, so that it doesn't affect the power system, because if you take a lot of power at a very short time, it may affect the power distribution. The other 2 points are the power converter topology developed for grid scale energy storage system. And the final one is the power converter configuration to integrate renewable energy to grid. So now I'll discuss some of the research area that we have worked for past couple of years. So one is, so this is related to the grid support. So this slide shows the growth for next 10 years for different countries in the world. So based on the population, as the population will increase and we need more energy efficient buildings, there are three key areas that we need a lot of power, or the power electronics system. So the first one is the renewable energy and storage, because we have different renewable energy, solar, wind, and we need to integrate to the grid. So we need a lot of power electronics converters to serve that purpose. The second one is for building and the commercial facility. So we need lighting, air conditioning, heating. So for all these systems we need power converter, which can provide an uninterrupted power supply 24/7. And the third one is data center. As we are going for as we're now going to 5G, and over now next 10 years, as we pass more time with we will go maybe 6G and whatever maybe. And for that high power, for that system, we need a very high power converter, energy efficient converter. So that is also a emerging area of research, that is a power converter for data center. And for all this application, the main customer requirements are effective utilization of the installation area, because at the city center, the place is very the place cost is very high, like in Singapore, where there is a limitation in the place. So we need to install power converters at very narrow space, because every square foot of the space cost a lot of money. So we need a effective installation. We need effective technology which can reduce the converter size, and at the same time we need to improve the reliability of the system, so it doesn't shut down if there is any fault occurs, or there is a backup supply if there is a fault in one of the converter. And the third, or most important point, is the efficiency. So we need to have a high efficient converter so that the power requirement from the grid we can reduce. So for this application, for to have a more compact converter, we need to reduce the size. And most of the converter, we have seen that to interconnect with the grid, we need a low frequency transformer, which is 50 or 60 hertz transformer based on the region. And this transformer size is very big, which occupies around 40% of the total installation space. So the left hand side shows the application for motor drives application, and the right hand side converter is for solar PV application. So for the motor drives, we can see that the red box is a transformer, and which occupies almost 40 to 45% of the total panels area. And after that, we have the middle portion is the power converter. The size of the power converter portion is almost similar, like compared to the transformer. And we have a control panel which will have the breakers to connect with the motor. So if we can reduce the transformer size, that we can if we can reduce the transformer size, then it can drastically reduce the total installation space. Similarly, for the solar power application, we can see that there is a huge container box, and which contains the low frequency transformer. So if we can reduce the transformer size, then similarly it can reduce the container volume and the installation space. So here for the space reduction, so the transformer size reduction is a very critical issue, and due to that thing, there is a solid state transformer concept came into picture. And what is solid state transformer? Solid state transformer is basically a high frequency transformer which is placed in between a DC to DC converter. So in place of a one very low frequency transformer, in this type of technology, a high frequency transformer is placed in between the DC to DC converter, and in place of only one converter unit, Suppose in the motor drive system, we have one AC to DC and then one DC to AC converter. Here we have multiple units connected in parallel. So in case of one of the unit fails, the other units can still work. So it gives a wonderful, a great advantage of reliability in terms of reliability. So this type of system have basically two advantages. One is the space reduction, because we are now operating at a very high frequency, and as we go for very high frequency, it will reduce the converter size. So on the right hand topmost figure, it shows the size reduction with increase in frequency. So if you go if we operate the system at suppose 50 kilohertz frequency, it will reduce the size about 100 times. So these are basically the two advantages. One is the space reduction and another is the redundancy of the operation. So some of the critical challenges with this type of converter are in the hardware related. Cooling system design. We need a very efficient cooling, because there are multiple converters unit, and they are installed at a very narrow area. So we need to take out the heat very efficiently, otherwise it will increase the temperature and it may blow any of the units. And we are placing both the converter and high frequency transformer at a very close space and very close to each other, so the heat of the transformer can interfere with the heat of the converter unit and vice versa. The second hardware related issue is the high voltage insulation design for high frequency transformer. So as it is connected to 6.6 kV system, and at the input side, we have a low voltage DC. So we need to have a very high isolation between the primary and secondary side. So suppose for 6.6 kV application, we need insulation of 30 kV. So to achieve that type of insulation voltage, there are challenges in the transformer design to optimize the transformer size and at the same time to have a high efficiency. In the control related, the voltage balancing of the units is a challenging issue, because all the units are either connected in series, input is connected in series, output is connected in parallel based on the application requirements. So we need to maintain the power balance. We need to make a power balance of all the cell units, and in case of there is any fault in one of the unit, we need to bypass it and we need to replace with other units. So there are different control related challenges there. Then the improvement in the efficiency. So we need to improve the control, or we need to design a control topology in such a way that it can improve the overall efficiency of the system. Then communication between the cells, because there are so many cells, there will be lot of sensors to measure the voltage and current. So there will be lot of controlling wires coming out from each cells. So how we can optimize the number of sensing unit, and we can reduce the hardware connection, because as we add more number of sensor, it will reduce the reliability of the system. So we need to find a best solution for this type of application. And wide voltage variation range, because for solar application there is a huge voltage variation at the input side, and to keep a output voltage fixed at 6.6 kV to interconnect with the grid, we need a converter which can operate at a high voltage variation range. So so this slide shows the same thing that I have discussed in the last section. So the input is connected to the solar and the output is connected to the 6.6 AC grid, and each unit is having the similar configuration. So the primary side of the transformer is connected to a full bridge edge bridge converter, and the output is connected with a diode bridge. And this is the DC to DC converter can be either a LLC converter or a DAB type, but LLC converter is having better efficiency compared to DAB type. So for this application, LLC converter were used, and to interconnect with AC grid, the output of the LLC converter was connected with another HV single phase converter, HV converter, which generates a AC single phase AC output, and it cascades with the series connected units. So here is the configuration of the LLC converter that was used for this application. So as I have mentioned, the input side is edge bridge converter, and the output is a simple diode bridge. And the secondary side, we have another edge bridge converter, which is basically an inverter to interconnect with the grid. So for the LLC converter, as we know that it is having the highest efficiency at the resonant point, and if we deviate from the resonant point, it will have lower efficiency. But the solar, the power coming from the solar or the voltage is not fixed. It deviates at a large scale. So to keep if we maintain the DC link voltage fixed, we need to change the switching frequency. And if we change the switching frequency and it deviates from the resonant frequency, it will reduce the efficiency drastically. So a modified strategy was proposed. So here DC converter frequency was kept at a fix or it was varied at a very narrow scale. So the output, so with the change in input voltage, which was coming from the solar power, the output of so the input to the DC bus was changing. So we are basically modulating the DC to AC converter so that we can have a fixed AC voltage. So in place of changing the DC to DC converter frequency to regulate the DC bus voltage, we are basically modulating the DC to AC converter to match the grid voltage demand. So based on that control, we saw that there was a improvement. There was a reduction in the loss, so it was about 20%. And the converter was designed about 13 kilowatt. And here is the one of the cell unit that was developed here. And related to this, the cell unit design, there are two challenges. One is the high frequency, high power transformer design, including their insulation. And the second challenge is the type of DC to DC converter. So what is the best solution, this DAB type or LLC type? So these things depends on the application. If we need a high voltage variation, maybe DAB is the best solution. If we need efficient operation and we have a fixed bus voltage, then LLC could be a better option compared to DAB type. So here is again the transformer that was designed for this application. As we need a high insulation for this type of application, as it is connected to the grid, we have used a plate which isolate the primary and secondary side from each other. So there are different type of design techniques how we can make an insulation. So for this, for our case, we used insulation plate, which basically separated the primary side from the secondary side. Here are some results for the DC to DC converter for the resonant converter that we have used. And here is the efficiency curve in one of the cell unit. So the maximum efficiency achieved was about 9 to 98.38%. So yes, so here are few references that I have followed to prepare this slide. I'll share with Dr. Biju, then you can go through this article. They are very informative regarding the global trend in EV and the renewable energy market, and what was the growth for past 10 years and what we are expecting in next 10 years, and different countries, what are the policies they are taking. They are taking into consideration to achieve the global target as per Paris Agreement. Thank you. That's all from my side.
Okay, Radhika?
Yeah. Hello.
Hello, yes.
Yeah. Rakesh?
There are a few questions in the chat box. Who's going to share that?
Hello,
Yeah.
can you hear me?
Yes.
Okay, so some questions are there in the chat box. So let me read out it for you.
Okay.
Okay, what is SST converter?
SST means solid state transformer. Solid state transformer, this is a high frequency transformer concept. Like for normal utility grid application, we have 50 or 60 hertz transformer that you can see in your locality. So they are generally very big size and they are very heavy. So they are so if we use for any converter application, they occupies a lot of area, and it reduce the what do you call so it occupies a lot of area, and for that reason if we have any space critical application, then we can go for high frequency. And if we increase the frequency of the transformer, as we know from the transformer equation, the size can be drastically reduced. So the converting a low frequency transformer based technology to a high frequency based transformer technology, and that corresponding technology we call it SST, which is solid state transformer. Is it clear?
Okay, sir, thank you. So the next question is, um, how do the electrical related globally known companies take people for recruitment? Like, what are the main criteria they look into, and what are the basic skills required for that?
Sorry, I didn't get your question. There are some disturbance.
Okay, how do the electrical related globally known companies take people for recruitment? Like, what are the main criteria they took into, and what are the basic skills required for that?
Oh, okay. So it depends on the position. So if there is a hardware related position, they will see whether you have sufficient experience in related to the hardware, like you have experimental knowledge, what is your graduation level. So they specify that you need to have a bachelor's or master degree. And if it is a hardware related position, then they will see whether you have developed some concept or you have tested some converters or something. So basically is the application related, and it they will see in your CV whether you have sufficient experience on that area.
Yes.
Okay, hello.
Hello, yes.
Okay, so the next question is, what are the challenges as a power electronics engineer you faced designing EV systems?
Oh, EV system. So there are different standards now coming up. Uh, so you have and based on that standards, you have to upgrade our technology. So what is the main challenging issue is to how quickly we can charge your EV battery. So what we want is that in less than 5 minutes we need to charge a EV, and for that we need a high power converter which can push that much of power to the EV at a short time. So so there are technology related challenges which are still there, and different researcher or the companies, they are still working on that. So so the converter topologies, there are not many converter topologies in high power area like DAB, LLC. So we may need to find out different converter topology which can meet the requirements. Yes, thank you.
And the next question is, what is the present status of V2G and V2H concepts? Is this concept is still in near research papers or have practical installations?
V2G already there are converter. There are different converters already manufactured by companies and they are available in the market. So they are not as widely available as normal EV charger, but there are already available converters. You can check online and you can purchase if you need. But there are regulatory issues. So once you want to feed to the grid, you need to you need to find you check with your utility grid whether it is okay with them and what are the regulator challenges.
Okay, thank you, sir. And the next question is, what is the place of wireless power transfer in the proposed topology? How can IPT integrated to the topology?
That is an interesting question. So normal right now the all of the maximum of the battery chargers are like a conventional type. Like we need to connect a wire to the EV. So which is not a smart technology. Uh, but in future, and there are already few products available for wireless charging, and some of the critical issues or the challenges with this topology are the efficiency. So the efficiency is not as high as conventional type. So that's why they are not very widely available, and there are some safety related issues like if the person or the driver or the passenger having some heart related issues, so how it will affect their health. So due to this reason they are not very widely available, but I think that is a very smart solution that, compared to the conventional system, because you don't need to come out from your car and you can charge your car while sitting on it itself.
Okay. The next question is, what kind of challenges we can get in designing V2G or V2H systems in India, as there is no such systems is present in this scenario?
As I mentioned, V2G, so charging vehicle or the taking the power and feeding to the grid from the vehicle, the topologies are already in existence and the converters are already there. So there is not such a big problem in terms of the technology. But for vehicle to grid interconnection or feeding the power to the grid, in the utility scale there are issues, because if there are many, so there are 100 cars, they start to feeding power to the grid may collapse because it's not that strong yet. So there are regulatory related challenges, and once government put a proper regulation or the rules, then it may be fine to install this type of converter, but not now, I guess.
Okay. What is the status of T-type inverter in EV?
Yeah, T-type inverter is very popular in EV application because it is much efficient compared to I-type. So below 15 kV application is 1.5 kV 1500 volt application, it is very popular.
Okay. The next question is, what are the present research areas in electric vehicles area side?
Yeah, so as I mentioned that the topology is already there. So to operate a EV, charge a EV or taking the power from EV and feeding to the grid is not a problem. But to fine tune the technology, like improving the efficiency of the converter, to improve the power density of the converter with GaN or SiC based topologies, then wireless charging, capacitive charging, uh, then vehicle to grid interconnection, then regulatory related challenges, because there are not much regulation or standards available yet in many countries. So those are also some of the critical issues in this area.
Okay, sir. As of now, the questions are over. From participants, any more questions? You can put your questions on chat box. Okay, sir. So all of the questions are over. Thank you so much for your Q&A section. Over to you, Radhika.
So now it's time to conclude our vibrant and informative session. I would like to invite Professor Pravin James, Secretary of IEEE IEEE Joint Chapter, to express his gratitude by proposing the vote of thanks. So please.
Respected Dr. Bijana Madam, Dr. Biju Sir, Dr. Vasanthi Madam, Dr. Abhijit Sir. First of all, I really thank to Dr. Abhijit Chowdhury, researcher, Drive System Control Department, Hitachi Limited, for taking the webinar. He made his talk in a wonderful manner. He explained the EV component, EV scenario, and EV technical components of EV systems in a wonderfully. Thanks for taking the webinar on behalf of the IEEE Pulse Joint Chapter. Also, I thank to all the participants for attending the webinar for various countries. Thank you for all.
Thank you, Dr. Pravin.
Again from Biju. So it was very nice hearing from you regarding the EV and the renewable energy side. So it was very informative, and it helped in updating really the status in renewable energy. Thank you once again, Abhijit. So hope
Thank you, Dr. Biju.
yeah, hope you are supporting our future activities also, our chapter conference.
Yeah, sure, no problem.
Yeah, Dr. Abhijit, welcome to the upcoming conferences. Please do have a share of yours also with us. And for all the activities that we are going to go, please be associated with the joint chapter. Thank you. Thank you for such a wonderful talk.
Thank you, Dr. Biju.
Thank you. Thank you all the participants, and thank you for the team, the technical team who gave the assistance for having the Zoom and all those arrangements also. Thank you. Student Lexicon team, thank you, Alan and team. Thank you all the participants.
Thank you so much.
Okay, sir. Shall I end the meet?
Yes.
Okay. Shall I leave? Is okay?
Yeah, sure. Thank you.
Yes, sir.
Okay.
Sure, sir.
Thank you so much.
Thank you so much, sir. Biju, sir, shall I end the meeting?
Yes, Ravi.
Okay, ma'am.